Hello Year 8 Science. Welcome to our first video covering our topic of physics. We're starting with physics this term and we're going to start with energy. Last year you did a bit of physics on force. This year we're going to look at energy and how it relates to some of the things around us. Now, as a sort of heads up, this isn't like my usual videos where I have a script and I am specifically aiming to talk about certain things. This is just me going through the same material I present to you in class, just instead of getting to look at my beard, instead you get to look at my hands, or the shadows of my hands, and my tablet screen here. So this will complement the bookwork that is being sent home with you during this current time. However, if maybe you're watching this in 2021 and we're all back to living in the sunlight and having fun again, obviously you can use this as a reference to the stuff that we're doing in class. So let's get into it. I won't be pausing for you to take notes. If you do want to take notes on stuff, pause the video, copy down whatever you need to, especially in the stuff that I've marked as a pencil, and then go on from there. So let's get started with our topic. For our waltz here, we've got a few waltz here. We want to know, well, firstly, what is energy? We want to know what are the 10 types of energy, and then we want to know about the difference between active and potential energies. And the things that we're going to be looking for is that I want you to be able to identify energy types in common places. You can see this stuff around you every day. That's one of the really good parts about studying physics, is that it's right there in front of you pretty much every day of your life. We're going to learn about the law of thermodynamics, the first law of thermodynamics, and there's a couple of ideas here. I want you to be able to define energy, what's a transfer, and what's a transformation. Alright, so we'll go through those. So, energy is the big idea of physics. It's one of the core ideas that physics is based around, and it's what our entire life is based around. Right now you're studying so that you can get an education, you can go into a career that you're interested in, so that you can earn cash to buy nice things, but at the base minimum you need food. That's a type of energy. You need electricity for your home. That's a type of energy. And right now you're using energy to be able to see this video. Either your computer or your phone is putting out energy or using up energy to create the light energy that you can see and the sound energy that you can hear. So it's all around us all the time. So before we get into the content for your assessment and for the unit, I just want to talk about what physics is in the first place, because this is a question I get asked a lot. So what is physics? So physics is the behaviour of the universe. It comes from the old word for science, physical sciences, or which originally came from the idea of natural philosophy. And so that's what this categorization of science in the 1600s, people like Sir Isaac Newton, and some of the others I would have heard of, like Dalton and Rutherford, Albert Einstein you've probably heard of. These guys that were categorizing the world around them and looking at mathematical stuff. And they started with the physical world. Things like movement, heat, sound, light. We also look at things as big as stars and as small as atoms, and it's about figuring out rules. We have a lot of mathematics in physics, and while mathematics is very prevalent through a lot of science, most of the big math comes about because we need it for physics. Right now we're all stuck at home because of this pandemic. Back in when Isaac Newton was born, 1600-ish, there was also a huge plague and shut down the university that he was in. So same position we are, but he didn't get to go home and watch YouTube videos and chat with their friends on Skype and play Xbox games. He sat there and looked at the stars, and he tried to figure out how planets worked and designed a whole new branch of mathematics called calculus, so that he could do the math probably a little bit easier and make sense of it. So math and physics works together quite a lot. And here's a little comic I like to whip out every now and then. Sociology, the study of societies, and psychology is the study of a person. Biology is the study of life, and chemistry is the study of atoms and molecules and how they do reactions with each other. And then physics is the study of all these things, and atoms just part of that. But then we've got the mathematicians all over here, because they're quite abstract. In fact, black holes, you've probably all heard of those. They were predicted by a mathematician well before we ever observed it, because the math said, hey, there's probably something out there that sucks up all light. So, mathematicians kind of there is a bit more pure, but the physicists like to say, no, you guys are just too abstract. So, let's get into the topic. And as I said, I'm not going to pause for you to take notes. You can pause the video yourself. So, energy means you can do work. And that really just creates a new question for you. What is work? What do you mean by work? Like, do you mean, go to work and get some money? Like if I ask you, have you been working out? You go, oh yeah, you can think about heavy lifting and you feel tired. In the simplest moment, in physics, work means something is moving. Okay, so if something is moving, there has been some work. And another really good example is when things heat up. If you make something hotter, you have done some work to it. Okay, because if you think about your stove or your microwave and putting food in there, the food comes out hot. Okay, and yeah, it's been spinning around in a circle, but it's not the spinning around that's making it hot. It's these microwaves, it's this light inside that little box there that you can't see because it's not within our range of sight. But that light is making it hotter, and that heat, that shows that some work has been done, some energy has been applied to it. Okay, so energy just means that we can make stuff happen. Movement or heat, those are the two big ones I want you to focus on at this stage in your studies. So, what are some types of energy? Now, it's a little bit hard to pair and share with some people. Perhaps you've got someone at home. Maybe grab someone to come and watch the video with you. Now, what sort of energies can you think of? Now, if you have access to your email, send an email to your teacher. Give it a go. So I think I'm up to the think, pair, share. I think these are the types of energy around us. Okay. Now, if you've already studied your notes or you've gone through the video before coming back to this bit, that's okay. Okay. Tell us which types of energy you can remember without going back to check your notes. Okay. So, physics, we're going to look at 10 types of energy. And realistically, you should try to remember most of these. Most of these are just common things around you. There's a couple of tricky ones that are not things that you'll really see much in your day-to-day life or be aware of. But give it a shot. Give it a shot. Try to remember all 10. Okay, so the 10 are kinetic. Now, kinetic just means movement. It's a fancy word. It comes from an old Latin word. No, kinesis might be Greek or Latin, I'd have to double check. But kinetic energy, it means moving energy. Some texts will just call this mechanical energy, or they'll say mechanical energy is machines and active energy is for organic things. We're getting rid of all that. We're going with a nice, easy, simple thing, just kinetic. Okay, it just means movement. Down the list, we've got gravitational potential energy. Anything lifted up high has gravitational potential energy. So this weight we can see up here at the top, well, it's not moving, it's standing still. But if we cut this rope, it will start to move. And we just said a couple of slides ago that energy makes things move. Well, if this thing's sitting up here and it starts to move, something must be making it move. Okay? And as such, it has some sort of energy stored. Okay? And then it has kinetic energy when it starts to move. This is examples of chemical potential energy, batteries and food. Okay? These are things that we store energy with. Food obviously stores energy for us. Batteries, you might be watching this on a phone. You've got a battery in that phone. It's storing energy that slowly gets used. You might have a remote control, probably for your TV. That would have some stored energy that slowly gets used. Eventually the battery goes flat, you've got to recharge it, or you've got to get some new batteries. Elastic potential energy, anything stretching, springs, rubber bands, those are the two big ones. Anything elasticy, grab a sock, stretch it, flick it at somebody. Yeah, that's elastic potential energy. But it also for anything that compresses. So if you think about the shock absorbers on your car, okay, or the really big ones on the buses and the trucks you see around you, okay, those springs actually compress to absorb energy, and then they re-extend to use that energy to do a little bit of work. So some springs are a little bit different from elastic in that they have compression and stretching, while with rubber bands, like the ones you shoot at each other, they're just going to be straight stretching only. Now these ones, this is the sun through an orange tint, and this is an example of a nuclear weapon there. But these are both examples of what we call nuclear potential energy. Okay, the sun is taking energy that is stored in the bonds inside your atoms, not the chemical bonds, like we learned a little bit about in chemistry last term, but the actual potential for energy inside your very cell, inside your very atoms, the little bits that make you up. You have nuclear potential energy in you. The chair you might be sitting on has nuclear potential energy in you. The floor beneath your feet, nuclear potential energy. The air around you, nuclear potential energy. But it's very hard to get it out, which is why it needs to be in these extreme circumstances, such as a nuclear weapon is a very extreme event of heat and pressure, or the sun is a very extreme event of heat and pressure. So if you go outside, glance up at the sun, don't stare at it, just glance at it. You will see that there's this massive ball of matter being slowly converted into energy. And if you've ever heard the famous formula from Einstein, E=mc², gets thrown around a lot on television shows like The Simpsons, etc. That formula is talking about nuclear potential energy, the energy contained in matter. Down the other side, we've got sound. Sound is a type of energy. You think about it, if you've got your phone or an iPod and it's not showing any visible things, but it's still playing music, well, the battery's going to go flat eventually, isn't it? So there is something, there must be energy in sound for those batteries, that chemical potential energy, to get flattened over time. Light is very much a type of energy. Some light is really intense. Lasers, for example. There are some great lasers out there that you can use to basically light up the sky. You've got to be a member of an astronomical society or something like that to show that you have cause to have them. But you can get some fantastic lasers out there, and they will heat things up. And when we talked about at the start, that heat is a form or an example that some work has been done, that energy has been moved around. Speaking of heat, heat's a type of energy. And then second last on our list is electrical energy. Lightning, the electricity running through my tablet here, the electricity running through your headphones or your speakers so that you can hear my voice, the electricity running through my microphone so that I can record my voice. Electrical energy is really important to our day-to-day life. And the last one on the list is magnetic potential energy. If you've ever seen a magnet move things around, well, the only thing that's doing is using magnetic force, so there is some energy going on there. Okay, so on a day-to-day life, kinetic. If you're doing anything apart from just lying in bed, there's kinetic energy there, isn't there? Sound, light, heat, electricity. You use those 5 here on the side every day. Okay? Gravitational energy. Glenala's at the top of a hill. If you walk up that hill, you can feel that gravitational energy. You can feel yourself getting tired. Going down the hill at the end of the day, that's a bit easier. Okay? If you're riding a bike or a skateboard, it suddenly gets a lot harder there. You're riding up a hill, you feel that energy, you can feel tired. But going down the hill, hey, that's a lot easier. Chemical potential energy, the food you eat, the batteries you use. Elastic potential energy, might not use that too often, but perhaps, a bit of elastic in your shorts. Okay, hold them up. What else do we have that's elastic on the day-to-day? Those automatic closing doors. Okay, so doors that pull shut by using a sort of spring load on it. We have a couple of those in the school, especially the library ones. They've got a tension, a spring in it. It might be a vacuum, but it's still the same idea of elastic potential energy. Nuclear potential, well, even if you don't think about it, you're looking up at the sun. That's there every day. It's lighting the way for you to get around. It's warming up the air around us. It's giving energy to plants so that we can chop them down and eat them. It's part of your day-to-day life. magnetic potential is about the one that you don't see much of in your day-to-day life. You would use it, anything that produces its own electricity through a generator generally has some magnets involved in it, but they're not things that you really notice very much. Oh, I'll go back a second. Now, notice down here, oops, go back. Notice down here there's a reference to a video. Now, I've provided access to my video storage on the eLearn system. So if you're watching this online, you can access eLearn, you've all been added, you'll be able to then access the videos. You just log in with your student username and password. I don't see your password, it's just because it's through the school storage system, and that way you can watch those videos that I've kept aside. This is lecture 1, so any of the videos that start with a 1, they're going to be connected to it, and generally the title is written there as well, so you can see there, what is energy. Now, the other thing about physics is physics, as I said, really likes math, and so all those energies that you just saw there, they have equations, they have math formula to describe and let us calculate how much energy there is. Now we're going to do a little bit of work with some of these just to give you a bit of numeracy practice. You're not going to need them for your assignment at the end of this topic, but we do want you to sort of see what it's like. For example, this one here, KE, kinetic energy, and if we know the mass, how heavy something is, and we know the velocity, how fast it's going, we can work out how much kinetic energy it has. Gravitational potential energy. If we know the mass, and G is a special number, 9.81 meters per second squared, and we know how high something is, we can work out how much energy it has. This one's light, this one's elastic, this one's for spinning objects, and this one's for how much electrical charge in a given area. So, or your distance away from electrical charge. Now, so there are lots of formulas out there, and those of you who like formulas, that sort of might catch your idea, because these are like the rules of the universe. Okay, these things are true 100% of the time. You might need some more understanding in other things. Okay, because for example, I might go, oh, but the kinetic energy doesn't make, like, the numbers don't add up. Well, there might be some rotational energy being taken up. And so if you know about its rotational energy and its translational, how fast it's moving, you can work out with incredible precision how things move and where things will go. Remember, like, we shot a satellite dish, and sort of a robot probe, about a 4-year journey through space, going around Mars and then back around Earth, and then back around Mars a second time, I believe, and then back around Earth again, just to get the speed to slingshot and meet an asteroid that was flying through space and land on it. Okay? That's like the equivalent of wherever you are now, closing your eyes, spinning around 5 times, and then throwing a toothpick and managing to land in my ear while I'm walking across the school. Okay, so that's a fairly precise throw when you think about it, isn't it? Okay, now I can't show you the videos through this because again, it's too much of an issue in terms of you seeing a good quality, because this works okay for things, but you're not going to be able to see a good quality video onto this through the camera, then onto YouTube. So again, access my OneDrive. There's 2 videos there, one called Rube Goldberg and one called OK Go. I think it says this too shall pass. And these are both wonderful examples of a machine called a Rube Goldberg machine. And I want you to look for energies. Okay, try to find as many types of those energies that I explained inside that video. Okay. And I want you to ask yourself, I want you to send me an email, send your teacher an email, okay, have a chat with your friend. What was happening with those energies? Okay, what were they doing? Have a good think about that before we go on, because it'll really help with the next bit. Okay, now let's go back to our types of energy for a second, because I want to draw your attention to the names. I want you to have a look at this column. I want you to have a look at this column. and ask yourself, what's the pattern that you see in these names compared to these names? What do you see as a big difference? Okay, now hopefully you sort of clued into it. Notice each of these are called something potential. Something potential, something potential, something potential, something potential, something potential. Well, these don't have the word potential. I like to call these ones active. They're energies that we see happening right now. In this very instant, you have some sound energy coming to your ears. This very instant, you might be moving your head around, you might be shifting in your seat. I'm gesturing with my hands, as you've probably seen if you've ever been in my class. Okay? There's some light energy travelling to your eyes so that you can see the video there. Okay? If you're holding your phone in your hands, it might be getting hotter. There's some heat energy, the electricity is running through it. But the chemical energy, well, that's stored in a battery. And if maybe you're on your phone and you're lying in your bed, you're holding your phone above your face, well, you just know if your hands slip, that phone is going to crack onto your forehead, and you're going to feel like a right little silly git, aren't you? Okay? But as long as your hands are there, it's not moving. It has gravitational potential energy. It has the potential to do something if everything else is in the right circumstance. So potential means storage. It means it can do the work, but it's not currently doing anything. It's stored. It's waiting. You wake up in the morning, you might feel a bit hungry. Hey, that's your body saying, hey, we're low on chemical potential energy. We can still work, but we might need to refuel a bit. I'm going for a drive and my car, the engine light turns on. So, hey, look, we can drive for a little bit more, but you're running low on potential energy. You need a bit more fuel to keep the car going. Okay? My phone sits there and starts flashing its red light at me. Oh, I need some more chemical potential energy so I can keep giving you electrical energy. Okay? So potential means stored. And all these other ones, I just call them my active energies because they're just things that are happening around us. Okay? So, now hopefully with these videos you saw a few active energies and you saw a few potential energies. And maybe you clued in that the potential energies get turned into active energies. Okay? So for example, something high gets knocked out of balance and starts to fall down. That movement knocks something else and it starts to movement. So the active energies get moved onto other active energies, but the potential energies get turned into other active energies. I've never come across an example where a potential, gravitational, chemical, elastic, magnetic or nuclear, gets turned into another type of potential energy before becoming something else. If you do find one, let me know, because that'd be great to add to my repertoire. Active energies, yep, they get converted, but I've never found a potential energy that can get converted into something else. And this leads to our first law. And it's got a nice, lovely sounding name, the first law of thermodynamics. Thermo means heat, and dynamics means movement, because when we look at things at a really small scale, and if you do any chemistry or physics in year 11 and 12, we do a bit of study of gases and the really small scales of heat and matter, we find that these two things are connected. Heat and movement are really connected together. And the first law says, in a simple form, energy cannot be created nor destroyed. It is only change form from one form to another. Okay? So we can move energy from place to place, we can change what it looks like, we can turn electricity into light, but the total sum of the universe does not change, ever. Okay? We can turn energy into matter, we can turn matter back to energy, okay? But the total amount is never, ever changed. And remember, we learnt a bit about matter at the start of this year, okay? That the total amount of matter cannot be created or destroyed. And this helped Einstein come to his understanding that matter and energy were the same thing, but they could be converted between each other with that formula, E equals mc squared. Now sometimes in text, the first law will be called the conservation of energy. And to conserve something means there's the same before as there is after an event. So if I hold... maybe you're in Xbox, right? And you're up in that mezzanine area and you're looking down at the Year 9s playing badminton, and they hit their shuttlecock up really high and it lands next to your feet. Now you're holding it over the edge, you're going to drop it back to them, and you let go, and the shuttlecock starts to fall, it gets faster and faster, and you're like, oh, it's moving faster, it means it's getting more energy. So it's creating energy, but it's not creating energy, because the energy that it has in its movement, it got out of gravity. But how did that energy get into the gravity? Well, the energy got into gravity when one of the kids hit the shuttlecock and gave it some kinetic energy and went up in the air and slowed down and eventually stopped. Okay? Not stopped hovering in midair, but stopped and landed next to you. Okay? If you perhaps have a largish book, something with a hard cover there, and you've got a floor that's slightly slippery, carpet's really good for that, or if you've got a trampoline, the nylon's really great. If you've got hardwood, you in socks would be really good if you've got hardwood floors. Slide across it and things slow down. And go, well, where's the energy gone? Well, the energy goes into heat. Rub your hands together and you'll feel them get hotter. That kinetic energy, that movement, gets turned into heat energy. Okay? So all the energy is all around us. They never vanish. It just gets turned into something else. Okay? It will eventually leave the planet because the planet gives off heat energy, okay? And that gets radiated out into space. Okay? But the total sum of the universe doesn't change. So this gets us into transfers and transformations. As we just said, energy is not still. It moves and changes every day, every minute, all the time. Okay? Even for you to hear this involves an energy change, electricity into sound. To see it, electricity into light. Okay? And because things are never 100% perfect, they've always got a little bit of inefficiency in them, or a lot of bit of inefficiency for some cases. Some of that electricity is becoming heat, and your phone might be getting hotter, or your computer's getting hotter. Okay? That's why if you think about the computer labs at school, we have a bit of air conditioning in those rooms, because if you've got 28 computers on, that's putting out a lot of heat. Okay? That electricity, some of it gets wasted and turned into heat, and the room warms up. So, two terminologies. One is called energy transformation. When we change one form to another, it is a transform. Okay? Trans meaning change, form, shape. It's changing what it is. It's changing what it looks like. It's a transformation. Okay? Now, as I said, there is a video for that. Have a look at it. Now, transformation does not mean these, even though they are changing shape. Okay? We're more talking about something like this. Your car transforms chemical energy into kinetic energy. Okay? A tree. Now, they've used the word radiant. I don't really like that word radiant. A tree changes light energy into chemical energy and gets stored in the leaves. Here's that word mechanical energy that I've said don't like there. Okay, hammering a nail, the kinetic energy of you swinging that hammer, okay, creates a bit of heat energy. It does make it a little bit hotter, okay, but it also moves the nail and it moves the pieces of wood apart. The sun, the nuclear energy in the hydrogen of the sun becomes light and heat. Electrical mixers, or all your electrical appliances, okay, turns electrical energy to mechanical. As I said, I don't like how they use the word mechanical energy for machines. It's kinetic energy. It's things that are moving. Okay, so kinetic energy and heat energy. Lamps turn electrical energy to light and to heat. So these are all around you all the time. There's a few, as I said, a couple of videos on that. Have a look on that. And the other terminology we need is an energy transfer. Now, an energy transfer is when a type of energy moves from one place to another but doesn't change what it is. So, two great examples, and they're in your home right now. We're cooking. Okay? Now, your hot plate, you might have gas like me, you might have an electric stove, you might have a fancy magnetic induction stove where they use electromagnetic induction to heat up the iron of the pot. You've got to use special fancy pots for it straight away. But again, normal pots don't work on it. It needs to be iron. But whatever it is, that pot is getting hot. Now, for those first two examples, the gas or the electrical stove, where you have some element that heats up, well, that bit on the bottom gets hot, and then that heat makes the bottom of the pot hot, and then the bottom of the pot makes the food get hot, whether that's water with your rice and your pasta, or perhaps a soup or a sauce of some kind, or perhaps you're cooking a bit of chicken on a fry pan. It's heat being transferred into heat, being transferred into heat. Okay, so it's an energy transfer, not a transform, a transfer. If you pop your head outside, have a look at the power line. There's electricity running through that. And then that electricity in that power line transfers to the line that runs into your house. And that runs into your fuse box. And then that transfers into the wires that run out to your wall sockets. And then that transfers, you guys getting the point here, into whatever machine, computer, phone charger, microwave so you can see the time, fridge, really big one there. Okay, it transfers the energy into those devices, and then they do a transform to make it into something useful. We don't really want just things just shooting electricity at us. That doesn't do much, but we do want it to transform that energy, that electrical energy, into something we can use. Now, there's another video there on energy transfers. Feel free to have a look at that. Now, as I said, physics is all around you. A little bit of homework. Okay? Now, I know you've got the booklets. I don't know if this is including the booklets. I haven't looked at it that deeply. But I want you to think about 5 things at your home, at school that you remember, the world around you. Okay? Something that shows one of these, each of the active energies. Tell me something that shows kinetic energy. Tell me something that shows sound energy. These things are in your home. Okay? And don't just look at machines. He's being quite quiet at the moment, but when my cat wants food, he demonstrates a lot of sound energy because he meows his head off. Okay? The cat has sound energy when it meows at me. Okay? Nice and straightforward. So you have these things around you. Okay? Go give it a go, and we will catch up with you soon. Stay safe. Have a great time. Bye.